Okay, we have 4 people, so there's still a small class. So make it ask questions, and don't feel shy of stopping me. So I'll start recording. Okay, thanks for showing up. Hey, what I want to do today is to cover, 6 points. This lecture is on fixed points of, you could say, a theory of fixed points that talks about fixed points of functions that are defined over complete lattices of functions that are monotonic. Okay. And they have these fixed points of such functions have interesting properties, and they form the foundation of automating horse-style proofs, of formal semantics, of model checking, and lots of other things, including type theory and structural induction. You might have already seen this in, I don't know if in this form or not, but you would have, I'm sure, heard about it. Okay, now in the class, you've already seen a few instances where I have expressed computation of reachable sets, computing reachable sets symbolically as computing fixed points of appropriately defined higher order functions over sets of states. One of the things that I covered in class, I don't know if you were there in the class or not, and there was a question about using, it was about, in the class that I covered was how the strongest post condition of a loop, of a while loop of this form. You can see the screen, right? Screen is visible.
Yes, yes, yes.
Okay. Of a while loop of this form, okay, where there is a loop entry condition LC, and the body is itself expressed as a transition relation. The body can be the strongest post condition of this thing, given some, a precondition, which is expressed as init of S. That is the condition that holds good at the head, prior to entering the loop, could be considered, could be computed as iterative computation, image computation. Okay. Until you reach a fixed point. And that's, I showed it as something like this, okay? So here, what I've shown here is each step of that iterative process, okay? You start with the set of the states that satisfy the precondition in it. And then you compute one-step image of that set in it as under T, okay, assuming that you enter the loop. That is one-step image of the relation if else, the transition relation, which says if the loop entry condition holds good, then you have TSS prime. So that computes the image of all the successes. Image means the set of all successes under such a transition relation of the init. Okay, that is all the states that are exactly those states and only those states that are reachable from init as a result of executing the body once, that is after iteration 1. And then that's what I'm adding to the initial set, and so on. The next step consists of computing image over R1 and so on until you reach a fixed point where you're not adding any more states when you have Ri plus 1 is equal to Ri. Okay. Now this, so this is what? So this is this set of all reachable states, and exactly those from some initial set of states, which is a precondition of while, can be expressed as a fixed point of a higher order function that keeps adding images, okay, one-step image, two-step image, etc., until it is not able to add anymore. And that is what is fixed point. Now, similarly, weakest precondition, K-induction, and several other model checking can all be expressed as fixed point computations, as procedures to compute fixed points of suitably defined higher order function. I say higher order because it is a function that manipulates formulas representing sets of states. It's a function from set of states to set of states. Okay, so and therefore, since all of them are, mostly iterative computation, so it would be useful. Another example, before I get to that, is you've already seen, is one of K induction, where happened. No, not this one. So here you saw how what I just now described was the computation of the strongest post condition, which is exactly the set of reachable states starting from initial state as expressed as a fixed point. K induction pretty much computes this one. Okay, it starts from a property P, and we showed that how it works was effectively by removing one, it's what are called counterexample to induction, one-step counterexample, and then two steps, etc., until you reach a set which is like one of the, something that is inductive and also includes, and it implies P, and it includes the set of all reachable states. So as you see, that can also be viewed as a fixed point computation that instead of adding images like here, it removes some things until it cannot, there are no more states that can be removed because all of them fold into itself, and it is a fixed point of such a function that removes all the counter states that represent counterexample to induction. So this itself can be expressed as fixed points, and therefore that brings us to this thing. So it is quite useful and insightful to learn about what these fixed points are, what are some of those the properties of these fixed points, of the of the kinds of functions that are going to be useful for us to express these verification algorithms. Okay, and that's what I'm going to be covering today. Okay, any questions? So that is kind of a motivation. So now I'll go into this one. Any questions there? Okay. So we start with partially ordered domain, or partially ordered sets, introduce complete lattices, and monotonic functions over complete lattices. And what we are interested in are fixed points of such monotonic functions. Okay. And these fixed points, the computation of fixed points over appropriately defined monotonic functions are what that all the algorithms, verification algorithms, including model checking, static analysis, that we will be seeing, can be represented as. Okay. So, okay, so some of these things are, I'm sure are familiar to you, but I'll introduce them anyway. So what's a total order? A total order over a set P, where the order is represented, say, as less than or equal to, as a total order, is a binary relation over some set P. It is said to be total if it is, for every element of a pair of elements of P, it's total, in the sense either A is less than or equal to B, or B is less than or equal to A. It is transitive, and it is antisymmetric, that if A is less than or equal to B and B is less than or equal to A, then A and B are identical. Okay. Such in order is called a total order. For example, the classical less than or equal to relational operator on the set of real numbers is a total order. So all these numbers on real numbers are on in a chain which are related by less than or equal to. So a partial order is allows for incomparable elements. A partial order, here represented as this square less than or equal to, is a binary relation that is transitive and antisymmetric, much like total order, but it is it's reflexive, but it's not total. It allows for some pairs of elements to be not related at all by this partial order. Okay, so that's what makes it distinguishing from total order. So this also has chains, but it in P related by this, but they could be multiple chains, some elements on those chains, on two different chains, may be incomparable. That is, they are unrelated by this ordering, the partial order. Okay. So examples of partial order. Of course, any total order is also a partial order, because the totality implies reflexivity. Okay. So, for example, sequences of letters, subsequences of finite sequences of letters over some alphabet, where you have some ordering on the letters of the alphabet, forms a partial order. Okay, the prefix relation that relates to sequences of letters forms a partial order. For example, lexicographic ordering of sequences, because there'll be some sequences there that are not comparable. Okay. If you have a set of universe, say, for example, in our application, we are interested in sets of states on which the transition systems are defined. And if you have your domain, your set is the power set over some universal set S, that is, set of all subsets of that universal set S, under the subset ordering, also forms a partial order. So here, this less than or equal to is set inclusion. Okay, so that forms a partial order. Now, similarly, a first order formula, because any formula, as you know, represents a set of states over a set of states where the state elements are the model, right? That makes the formula become true. Under implication ordering also forms a partial order. Okay. So here, I mean, there's one small comment here, implication. These formulas, of course, you can have different syntactically different formulas that are logically equivalent. So equality here for the purpose of defining reflexivity and antisymmetry is considered a logical equivalence. Okay, with that, this formulas, the set of all first order formulas under implication ordering is also a partial order. So these kinds of things occur very commonly in practice. And for our applications, what we are interested in are fixed points of functions that are defined over such partially ordered sets that are represented by the last two bullets. Okay, that is what would be of interest to us. Any questions so far? Okay. So here is a graphical representation of a partial order. So here, the universal set is the set that contains 1, 2, 3, and 4. And the domain is, the elements of the domain are, I mean, the domain that is of interest to us is the power set, okay? The set of all subsets of these things, including the empty set. And the set inclusion is the ordering, okay? And here, every edge represents, the set inclusion ordering. So as you can see, there are some sets which are strictly, they're ordered, by the set inclusion, but some are incomparable, okay? And that's what is represented here. So this is a partially ordered set, and where the ordering is set defined by set inclusion. So when you have this, then one can define what is called a join operator over a partially ordered set, okay, of any partially ordered set. So this defines, okay, first of all, an upper bound of a set of any subset of this partially ordered set is an element U belonging to P, such that every element in that set is bounded by the that upper bound element, that every element in that set is less than or equal to the upper bound. Such an element of P is called an upper bound, okay? And, I mean, we're introducing join, and there'll be a dual operator called meet in order to define the domains that are structured in a specific way, which are called lattices, which you might have already heard, and that's what I'm in the process of defining, okay? Now, join the least upper bound. Okay, join is defined. This is a definition of an upper bound. The join is defined as the least of all upper bounds. The join is an operator over some subset of elements drawn from P, and that is an upper bound, but it is the least among all upper bounds. That is, if for every other upper bound U prime, for all upper bounds U prime of U, mu is the least upper bound, and that's what the join operator represents. Okay. Now, for example, in this partially ordered set that we saw, so what is the join that is the least upper bound? I use join and least upper bound interchangeably. Okay. So anyone, what is the join of this set 1 and 2?
One comma two.
Yes. Okay. Of course, there are other upper bounds 1, 2, 3, 1, 2, 4. Yeah. Okay. And the universal set is also. Okay. So that's good. Yeah. So here is, and this one is 2, 3, 4. For this particular case where the domain is the power set over some universal set with the ordering being inclusion, the union of those two sets will compute the join operator, as you might have guessed. Okay. So here for 1, 4, and 2, 3, what is the least upper bound of the join? Yes.
1, 2, 3, 4.
Yeah. It is 1, 2, 3, 4, right? Because none of these things can at this level here can serve. So it's 1, 2, 3, 4. Okay. Similarly, you can have the dual of join, which computes the greatest lower bound. Okay. So a lower bound of a subset of a partially ordered set is something which is bound from below. Okay. So it's an I belonging to P such that I is less than or equal to every element in that in that set. Yeah. So the greatest among all lower bounds is called is defined as the meet. Okay, and it's denoted like this. Yeah. Yeah. So like I said, for power set, the join operator is the set union, and the meet operator can be computed by taking the intersection of those things. So for Boolean formulas, set union is equivalent, is the same as taking disjunction of those formulas, and meet can be computed using by conjoining those two formulas in the thing. So here it is taking the superminimum or a maximum or the minimum. Okay. So for example, here for the partially ordered set of reals over less than or equal to, so this one is 1.3. How about the meet of 1 over n? Anybody? N belonging to n. This set here, it's an infinite set here, okay, but a subset of R. So here I'm asking for the greatest lower bound, okay, for this series 1 over n, where n belongs to n. It is 0, right? So it is that's an infinite series, but 0 is bounds from below those things. For R, it is for the real set. Okay, it is minus infinity is the meet, and plus infinity. And of course, in some situations, minus infinity and plus infinity are not included in R. So in some cases, the join and the meet may not be in that set, okay? There are some tricky cases. You can think about these things. One is, this is kind of a corner case. If it's an empty set, every element R is a lower bound. Since empty set has no element, everything is there, and therefore the greatest among them is infinity, and that is what is defined as the thing. So the point is that a meet and join, sometimes they may not, of some partially ordered sets may not is not always guaranteed to exist, okay? Because we insist that meet and join has to be some element present in the partially ordered ordered set, okay? So they may not exist in for all partially ordered sets. Yes, and they may not also be unique, okay? So, yeah, a semi-lattice is, okay, when you have less than or equal to something where,
Sir,
yeah,
I had a doubt on a previous question.
yes.
In the second one, that 1 by n belongs to n, but 0 doesn't belong to natural numbers, right?
No, no, here R is a real
Oh, okay, sir. Sorry.
of reals, okay?
Okay.
Yeah, yes, okay, the set of all reals, because 1 over n, 1 over n is fractional, no? I mean,
Oh, yes, sir.
rational number there, yeah? Okay.
Yes, sir. Sorry, sir.
Yeah, a semi-lattice is, okay, a partial ordered set just is defined as a set of elements ordered by a partial order, okay? If you add the join operator, that is called the join semi-lattice. Similarly, you have the meet semi-lattice, okay? A semi-lattice with a join operator is said to be complete if this condition holds good. So it's a complete lattice if every non-empty subset be of of the partially ordered domain is guaranteed to have a join, okay, belonging to A. Okay, when I say it exists, I mean that every subset has the least upper bound. The least upper bound exists in the as an element in the partially ordered set. Okay, so for example, as we saw in the previous case, less than or equal to, if you add this infinity in to R, if you enhance the real set by including infinity, then of course every subset of R is bounded from above. Okay, that infinity is every set has every subset, including the set of all real numbers, has an upper bound, at least upper bound. Okay. Similarly, you can have the meet semi-lattice. Okay, if you add the meet operator, and with the requirement and make it correspondingly, you have a completeness definition for that semi-lattice, which requires that every subset must have a meet belonging to the partially ordered. Such a semi-lattice is called a complete semi-lattice for the join. Now, a lattice is something which has is a partially ordered set which has okay, with a meet and enhanced with a meet and a join operator. It's, yeah, which has both join and meet. And that is complete if every subset of the partially ordered set, for every subset, there is, the meet and join is defined. Okay. So the power set under inclusion is a complete lattice where, because the power set has the universal set as an element of the domain and the empty set. So the universal set and the empty set can serve as the largest upper bound and the least upper bound and the greatest lower bound, respectively. Okay. So these two are complete lattices, as you have both a meet and join operator for all subsets of those things. Yeah, like I just now said, since a complete lattice always has, a complete lattice guarantees that the entire the set, which includes all the elements of the domain, should also have a top and a bottom element. The top element of the entire set, okay, of the set of elements of the lattice is denoted as top. And the bottom is the greatest lower bound of the entire set, which is the least element in the of the complete lattice. So, for example, for this R enhanced with minus infinity and plus infinity and less than or equal to partial, or it is top and bottom. For a power set, it is the universal set serves as the top element. So that's an element which is that is greater than or equal to everything in the domain, and the empty set serves as the bottom element. Okay. So any questions with this? Okay, so what we are interested in is, like I said, fixed points of monotonic functions, which we will define right now, over such complete lattices. Specifically, what we are interested in is the domain formed by the set of all subsets of the universal set over which our transition system is defined, okay? And when we want to represent algorithms that do reachability analysis and various model checking algorithms over such transition systems, that is where we need to they are going to be expressed as fixed points of monotonic functions, and that's what over that particular lattice, and that's why it is of interest to us to study monotonic functions and fixed points of such monotonic functions over lattices, which is what we will do now. Any questions? Okay. Okay, so let X and Y be two partially ordered sets, and F be a function mapping elements from X to Y. And we'll assume that it's a total function now, okay? Monotonously can be probably defined for non-total functions too, but let's, for our purposes right now, we'll assume that our functions are total. Then F is monotone or monotonic if this property holds true. If A is less than or equal to B for every pair of elements in X such that A is less than or equal to B, A and B are related by the partial order. When you apply FA and then FA, when you apply F to A and B, they should also be ordered, okay, in that less than or equal to order defined over the range. And this should hold good for all A and B in the domain of that function. Okay, so it's just that if okay, partially ordered says, as you know by now, have ascending and descending chains, right? So what this requires is if you pick an ascending chain in a partially ordered set and you map every element in that ascending chain into, by applying F to each of the element, then the result of such of application over the ascending chain will also be ascending, or if it's descending, it'll also be descending in the range after the map, and that's what this specifically implies. Yeah. Okay. So here are some examples that I want to. So say this function 2 to the x, is it monotonic? Anybody? It's
It is
Yes, sir.
yeah. Why?
So for any number x plus 1, 2 to the x plus 1 will always be bigger than 2
Yeah,
to the
even
x.
negative. Okay, the important thing
Yeah.
is negative also. Yeah, because if x is less than y, then when you do 1 over 2, it is also less, right? Yeah. Okay. How about this one, x squared?
No, that's not.
That's not, because it's kind of a parabola, right? On the negative side, it violates the monotonicity property. Yeah. Okay. Now here's a function defined over the power set. Okay. And with this function is for any m from the power set domain, that is some subset of S, it is removing a specific element. This is small s, okay? Capital S is the universal set. This, you read this as a specific element from the universal set, and it is removing that element from M. Is this monotonic? I say it's not monotonic. Is there a counterexample that you can think of? You see, for suppose, yeah, yes.
Can you repeat the function definitions? The function definition of this.
Take some element from this power set domain, okay, and removes some specific element from it, okay.
Okay, sir.
So this is slash. The slash is set difference, yeah.
No, got it.
Yeah. So, for example, if you had 2, 3 and 1, 3, and if you remove 3, I mean, let's see. So maybe I say it is not, because as a result of removing one element, if it's less than or equal to that, then you may, as a result of removal, you may not remove something at all from the other thing you might remove, and it may cause, okay? So why don't you think about this, okay? I claim that it is not monotonic, okay, because it can result in incompatible sets, yeah? So you'll have to analyze the different
So
situations.
if we take two sets which have the same cardinality and one of them has S and another one doesn't have S,
Yeah.
then I think
It can violate. Yeah.
Hmm? It can vary.
But even then, if it is if it is a subset, then it will be less than or equal to. I guess this is monotonic. Okay. So yeah, even if one has that element, the other one does not have that element, since it is subset of it. So when you remove that, then you will at most get less than or equal to, right? Yeah. So I think it is monotonic. I was wrong. Yeah, this is monotonic. If it is, since it requires, if you are starting with something where say M1 and M2, and if M1 is a subset of M2, either M1, if you're removing, if S is the case where it is in both sets, in which case, if you remove, at most they can be equal, nah? So it is less, it will be less than or equal to. If it is in one but not in the other, even then, every other element is, yeah, if either the element is present in both cases, where you will still have less, it will be still subset, or if it removes something, then it'll at most be equivalent. So I believe it is monotonic. Okay, this one is indeed monotonic. Okay. In any case, if you think it's not, let me know if you find a counterexample. Okay, so more examples. Okay, so when we have specific lattices, so sometimes F is monotonic or not, you need to think a little bit. You can always prove it is monotonic or not with some thought, but I want to take a few kind of corner case, draw your attention to certain corner cases which you should be aware of. Okay, so here these are artificial examples. Okay, so here is the dashed edges are what defines the lattice. Okay, and the solid edge with an F labeled F, it defines the function, the mapping. So here the function is mapping both the domain and the range of the function is the same lattice. Okay, and it's a complete lattice, and therefore we assume there is a top and a bottom element. So is this function, it's a finite lattice, and therefore F I've represented as a set of edges. Is this monotonic? Quickly. See, here you can actually check now, because bottom is less than or equal to 1. Bottom is less than or equal to 1. So F maps this 1 to 2. Since bottom is mapped to itself, so both bottom is less than or equal to 1 and 2. So this mapping, although F is mapping into incomparable elements from one to the others, specifically 1 to 2, it still does preserve, okay, the thing. And also there is a descending chain here because 1 is less than or equal to tau. 1 is less than or equal to is this? Yes. Let's look at that. 1 is less than or equal to top. Okay, top is mapped to 2, but 1 is also mapped to 2. But 2 is indeed less than or equal to 2. Therefore, the tricky part here is F when it comes to 1 and 2, 1 is being mapped to an incomparable element, but it doesn't matter. Okay, in this case, the monotonicity is preserved despite a cross mapping of this kind. Sometimes that can get you into into trouble. And that's the point that I'm illustrating. So are you convinced that this is monotonic? Yeah, but as far as 1 and 2 is concerned, it doesn't matter because 1 and 2 are incompatible anyway. So the premise of checking F doesn't apply to that. So you will have to really check for those cases where for every pair which are of elements in the domain which are related by the less than or equal to. So here 1 is less than or equal to tau, and since 1 is mapped to 2 and bottom is, top is mapped to this, since 2 is less than or equal to 2, that is indeed, it preserves in all cases. Yeah, convinced? Anyone has doubt? Hello? No answer?
No
No
doubt,
doubt.
sir.
Huh?
No doubts.
Okay. How about this one? The only change here is I'm mapping bottom to 2.
So this is also monotonic. All of them are mapped to 2.
Well, consider, see, bottom is less than or equal to 1. So what is f of 1? It is 2. Yeah. Here that 1 at bottom is less than or equal to 2. Yeah, say f of 1. Yeah, so it is. You're right. Okay, so let's see of top. 1 is correct. So here
Or we
also
can directly say all the elements are mapped to the same element. So it will always obey the
correct.
opposite
Yeah, so
criteria.
this is the case. So here are 2 violations of monotonicity. Okay. Yeah, here it's violating because 2 is a violating element, okay? 2 is mapped to 2 by F, but bottom is mapped to 1, okay? So 1 and 2 are incompatible, and therefore that violates, okay? If you consider bottom is less than or equal to 2, but their images are incompatible, okay? That's why this one. And here's another case that violates monotonicity, okay? So here I'm assuming that top is mapped to 2. So there is an arrow of F missing here. It must be a solid F arrow from top to 2. And this kind of a thing, okay, anytime that you have these incompatible elements, you will have to be careful in the way that you structure the F. So here, this is not monotonic either, okay? Okay. So you see why this one is? Because see, yeah, the violating thing is 2 and bottom, okay? Bottom is less than or equal to 2, but the images are incompatible, and something similar to that happens here with respect to bottom, okay? So now I'll come to definition of fixed points, okay? And the main theorem, I will introduce fixed points, and I will introduce the main theorem, which is a theorem about when fixed points are guaranteed to exist, okay? So what are fixed points? Fixed point is defined for a particular function. Fixed points of a function f. In this case, we say it is mapped from X, both the domain and the range are the same. Okay, of course, the fixed points are defined only when domain and ranges are the same. Fixed point is an element of the domain which maps that element to itself. Okay, and the set of all fixed points are those elements, subsets of the domains which where each of them is mapped to itself. Okay, and for any given function over some lattice, you can have no fixed points or multiple fixed points, and even infinite number of fixed points. Now, the first result, these are the three main results, okay, that about fixed points, existence of fixed points for monotonic functions over complete lattices. Okay. Fix of f, the set of all fixed points of every monotonic function itself forms a lattice. Okay, maybe I should first introduce the second and the third bullet. Okay, so there exists the least fixed point of f and the greatest fixed point, both these exist. Okay, so first of all, because this itself forms a lattice, that is the first result. So, okay, the set of all fixed points of the functions itself forms a lattice. And since it's a complete lattice, that itself guarantees that there is a top element, that is the the bottom element, which is the least fixed point, and there exists a unique top element, which is the greatest fixed point. So as a result of that forming a lattice, this guarantees that these two fixed points exist. So this is where we saw that there was f is monotonic, right? As per that previous result that I quoted, that I stated without a thing. So what is the what are the fixed points here? First of all, what are the fixed points of f?
Bottom or 2 and 2.
Bottom is 1 and 2, correct? That's, 2 and bottom. So the least fixed point is bottom. As you can see, it forms the lattice of fixed points has just bottom and 2. The least fixed point is bottom, and the greatest fixed point is top. Okay. Here, of course, it's there's only one fixed point for this function f, and both the top and the bottom of the lattice of the fixed points are the same. Okay, which is 2. See, in this case, f is not monotonic. Although f is not monotonic, there are fixed points. Okay, fixed points do exist. Here, 1 and 2 are the fixed points of f, of the function f over this lattice. But as you can see, there is no unique least or greatest fixed points. Okay, that is not, so for monotonic functions, the greatest and least fixed points exist, but here they are incomparable. Okay, so I'm just showing you an example. So non-monotonic functions, the non-monotonic functions, the greatest and the least fixed point may not exist, even if they do permit fixed points. So here is another non-monotonic functions. Here, there are no fixed points at all. Okay, so whereas for monotonic functions, it's guaranteed that they have fixed points, because the greatest and the least fixed points exist. Okay, so that's the main crux of the thing. So this is where I'll stop, and I will. Okay, I mean a couple of more slides. Okay, the proof of this main theorem, which is kind of the fixed point characterization, and there is a companion theorem. This is called the Tarski's theorem, which gives a characterization and indirectly guarantees the existence of fixed points, and by virtue of the fact that the set of fixed points of monotonic function themselves is a lattice. What this states is the least fixed point of a monotonic function over a lattice always exists and is given. Furthermore, it actually characterizes, it gives a characterization of the least fixed point. Okay, says that it is the greatest lower bound, that is the meet of all elements that exist on all descending chains. Red is called reductive, okay? Reductive F, where reductive F is the set of all X belonging to the lattice such that Fx is less than or equal to X. They are elements on all descending chains defined by the partial order less than or equal to over the partially ordered set. Okay, and the greatest lower bound of the entire set, if you just compile all the elements on all descending chains, the greatest lower bound of that is the least fixed point, is what Tarski's theorem says. Okay, so it is the smallest element. If you look at all the descending chains, because the descending chains, they are all related by the less than or equal to operator. They cannot keep on going forever because it's a complete lattice. There comes a point where F does not add anything. You will hit some minimum element. Okay, and that is a fixed point, is a fixed point of F. Now, if you collect all such elements over all descending chains, and if you compute the greatest lower bound of that, and that is the least of all fixed points. Okay. Similarly, there is a dual version of this Tarski's theorem, which characterizes the greatest fixed point among all fixed points of a monotonic function defined over the lattices. What it says is the greatest fixed point always exists and is given by the join operator of all elements over chains that are extensive, that is, elements on all ascending chains. If you collect all the elements on an ascending chain, and if you take the least upper bound of that, then that gives you the greatest fixed point. Okay. Now, yeah, these are examples that you can follow. Okay, that you can, I mean, you can see that in the case where the two situations where it's F is monotonic, you can work it out and you see, Tarski's theorem holds. But where I will end is with this slide. Okay, this is what the implication of Tarski's in a pictorial fashion. So here is the lattice, this set that I have. Okay, it's a lattice, and therefore it's a partially ordered set with a top and a bottom. Okay, so the top subset that I've shown here are where all the descending chains reside. Okay, so all the descending chains. Okay, these are the reductive elements, this top one subset here. Similarly, the bottom subset of this complete lattice is the extensive set, the set of all ascending chains. Okay. And where those two intersect is where you have all the fixed points of this monotonic function f residing. The sliver, which is the intersection of all the set of all reductive element sets and the extensive element sets, is where all the fixed points lie. And Tarski's theorem, as a corollary, it says, says that it has there's a greatest fixed point of that, and there is a least fixed point, because they themselves form a lattice. And the greatest fixed point can be computed as the greatest lower bound of all descending chains, and the least fixed point be computed as the greatest, the least upper bound of all. The least fixed point can be computed as the greatest lower bound of all descending chains, and the greatest fixed point is computed as the meat, which is the greatest lower bound of all ascending chains. Okay, so so you can make examples of these things and then verify yourself, convince yourself that Tarski's theorem indeed holds good. But we will have I will go through a proof of this in the next class, and we are not meeting on Friday. We'll be meeting next week, Monday. Okay. That's the end. Unless you have any questions. Any questions? Okay. Yeah. So I'm going to stop recording. There are no more questions.